All right, let's take another look at multi-body systems and do some examples with them. This is a Atwood's machine. The point of an Atwood's machine is that it's not anything especially difficult or complex. It's not really useful as a machine. It was something that this guy designed, George Atwood designed, in order to teach students about acceleration. So in this case, we have two objects hanging over, tied to each other, hanging over a smooth cylindrical surface that's pointed at us. Or you can imagine that they're taken over, say, a massless pulley. If I were to let go of A and B and just see what happens, what would you assume would happen if they start out initially like this with me holding them and I release the two of them? Some people might assume that A would go up and B would go down because they're equal masses and they should be at the same height, and that's not correct. If you're not sure about that, I'd like you to see if you can arrange some sort of experiment where you test this out yourself with two equally weighted objects tied to each other over string, wrapped over top of some smooth surface like this. But hopefully you're able to analyze this and say that the gravitational force pulling down on A and the gravitational force pulling down on B are equal to each other. So there's no reason why this system would get pulled more down on A or down on B. I think people have a tendency to think that these two will equalize because that's how it works when you're doing things like working a balance. You know, in like a lab class, you put a certain number of grams on one side and a certain number of grams on the other side, and you want it to balance out. That's not what this is. In this situation, these two objects will only accelerate if one of them is more massive than the other. I do want to note I just put a hash mark through the force of tension on each of the blocks to emphasize that these two blocks are tied to each other with a single rope, and that single rope will have a single force of tension throughout it, pulling in both directions. The force of tension pulling up on B and the force of tension pulling up on A are the exact same force by Newton's third law, and that will matter a lot when we go to calculate what's happening in an Atwood's machine. Given an example like this one, if you had to predict the motions of objects A and C, I think you would all correctly predict that block C will fall and block A will go up, and that the acceleration of block A upwards would equal the acceleration of block C downwards. It should be noted that that acceleration would have to be something less than 9.8 meters per second per second. That's how fast block C would drop if you cut the string. So as long as A is tied to it, it'll be some acceleration less than 9.8 meters per second per second. But we know the directions already. Let's take a look at what happens if you have to draw the free body diagrams for them after they've been released and talk about the magnitudes of the forces on the two free body diagrams. Block A has a gravitational attraction to the planet Earth, so it's got this downward gravitational force on it. It also has a tension force pointed upward on it, and when you go to draw that in, ask yourself, are these two forces the exact same size? And the answer has to be no, because you know block A is going to accelerate upward. So the tension force upward must be more than the gravitational force downward on block A. Now, as we mentioned in one of the previous problems, you might be tempted to say that the tension force pulling up on A is the weight of block C. But let's take a look at block C. Block C has a tension force pulling up on it, and that tension force pulling up on block C is the same as the tension force pulling up on block A because it's the same string. But block C is accelerating downward, so the tension force pulling up on A can't be equal to the weight of block C. The gravitational attraction of the Earth on block C must be larger than tension in order to make block C drop. So in an Atwood's machine, it is important to recognize that the force of tension pulling up on the lighter mass has to be more than the force of gravity pulling down on the lighter mass, but also less than the force of gravity pulling down on the heavier mass. It has to be some value in between the two of them. All right, let's take a look at what you would need to do to calculate the acceleration of the Atwood's machine. I'm going to show you two ways to do it. One is a little bit lengthier and more mathematically precise, and the other one is a little bit quicker, but you'll have to make sure that you understand how the second one works before you try to use it. In either case, you'll want to draw a free body diagram of each of the blocks individually, and you'll want to note that the acceleration of the one block is related to the acceleration of the other block. You can say that they're the same acceleration, but technically they're only the same magnitude of acceleration, because one of these blocks is accelerating upward and one is accelerating downward. So one is positive and one is negative. And of course the force of tension on the two blocks is the exact same amount of force because it's the same interaction. So I start with my mass A, which we have a free body diagram of, and I know that the net force acting on mass A equals the mass of mass A times its acceleration. I know that the net force acting on mass A is the tension force pulling up minus the gravitational force pulling down, and that equals mass A times acceleration. I can solve that for the force of tension as the gravitational force on A plus mass A times acceleration. And since the gravitational force on A is mg, then this ends up turning into force of tension equals ma times g plus a. This should look really familiar. This was how we calculated the scale force, the normal force, on an object in an elevator. And the same thing is true here. For mass C, we'll get the exact same type of situation, but I know that the net force equals mass C times acceleration of C, and I know that the acceleration of C is downward. It's the same value, but the negative of the acceleration that was upward on mass A. So I would have to put the negative in here. I could then say that the net force on C is the tension force pulling up minus gravitational force pulling down, and that equals, I'm going to distribute that negative out front there, negative mass of C times acceleration. I then solve this for the force of tension, and I get that it's equal to the force of gravity on C, which is, of course, mass C times G, minus mass C times A, and I can turn it into something that looks like this. This is very similar to what we had when we were talking about elevators that are accelerating downward. But I want you to notice I have two expressions for the force of tension here. Force of tension equals mass A times G plus A, and it also equals mass C times G minus A. And those two A's are both acceleration. The same exact acceleration value. It's just that one is up and one is down. So I can set those two terms equal to each other since they're both force of tension. The reason that that's useful to me, I'm going to distribute these masses. And then I'm going to add the mc times acceleration. And then I'm going to take that rightmost term, the mass of c times acceleration, I'm going to add it to both sides. And then I'm going to subtract mass of a times g from both sides. So what I've done is I've consolidated mass of c times acceleration plus mass of a times acceleration on one side, and mass of c times gravity minus mass of a times gravity on the other side. And the reason I want to do this is because I'm trying to solve for the acceleration. I want to get the acceleration terms together. So the acceleration can get pulled out on the left there. And what I determine, if I isolate acceleration by dividing both sides by what's in the parentheses there, the acceleration of the whole system, up for block A, down for block C, is the gravitational force on block C minus the gravitational force on block A. And that whole quantity is the numerator, which then is divided by mass C plus mass A, the total mass of the system. In this case, I know mass C and I know mass A, and I know G, so I can calculate that the acceleration of the system is 3.26 meters per second per second. It's up for block A, down for block C, which I already knew. The second part of the question was to ask us to determine the tension in the string connecting A and C. The way to do this is to take either block A or block C, it doesn't matter which, and evaluate it with the known acceleration that you have. So mass A, we know that the net force is equal to the mass of A times acceleration. We also know that because there's two forces acting on mass A, we had established that the force of tension is equal to the mass of A times G plus A, just like an elevator. And now we know the mass of A, we know G, and we know the acceleration, so we can put all of those in and determine that the force of tension is 2.612 newtons, pointed upward. And if we had instead opted to use mass C, we would have said the net force equals the mass of C times the acceleration. We know the acceleration of mass C is downward, so we would have made that a negative when we put it in. The force of tension on mass C is equal to the mass of C times G minus A, because it's accelerating downward. We plug the numbers in. Mass C was given as 400 grams, so 0.400 kilograms. And we get that the force of tension comes out to 2.612 newtons. Sure enough, the exact same value on mass A as on mass C, which is how it's supposed to be. So you could have picked either one. You don't have to calculate both. Now, as I said, the previous slide with the system of equations, that is a more complicated mathematical setup. An easier way to do the math requires a little bit harder conceptual vision of what's happening. I'd like you to reconceptualize Atwood's machine and learn how to do it this way, and then decide for yourself whether you would rather do it the previous way with the system of equations or the way that I'm going to show you right here. On the Atwood's machine, I know that block C is going to pull block A. I know that block C is going to drop and block A is going to go up, but I can visualize it like this. Block A is getting pulled in one direction, and block C is getting pulled in another direction. Now, they're both getting pulled by gravity, so in the original drawing, I could see that they're both getting pulled down. But the gravity pulling on block C fights with the gravity pulling down on block A. So I can try to visualize this as a system that's getting pulled in two different directions, and those two forces are therefore fighting each other. And so I could say that the net force on my system is the mass of my system times the acceleration of my system. The net force acting on my system here is mass A times G pulling in a negative direction plus mass C times G pulling in a positive direction. And that equals the mass of the system, which of course is mass A plus mass C, times the acceleration of the system. And I can therefore determine that the acceleration of the system is negative mass A times G plus mass C times G over the mass of the system, which is the exact same thing that I had in the longer version of the equation. I got 3.26 meters per second, which is the exact same value we found earlier. And I already knew that block C was dropping down and block A was moving up, so I know which one is moving in a negative direction and which one's moving in a positive direction on the original drawing, even though in this reconceptualization, they're both moving to the right. Now, in order to find the tension between the two, you still have to go back in and evaluate just one of the blocks, and you'll get the exact same value. And it could have been block C instead of block A. It wouldn't matter as long as you are careful about saying that on block C the tension is pulling to the left. This is a lot less math than in the previous method. But again, this requires you to look at this picture and say that that is an Atwood's machine, which it really doesn't look like. Whichever one works best for you is the one you should use. I'd like you to give it a try with this problem right here. I will put the answer to this one in the notes. On the screen here is a website simulation of an Atwood's machine that has been modified somewhat so that the blue mass M2 on the left side is not suspended vertically from the string. We want to learn how to be able to answer questions about a modified Atwood's machine that looks like this, but we will begin by taking a look at a version that is simplified a little bit more, making the surface that M2 sits on horizontal and frictionless. It's a very similar idea to what we were just talking about. You're going to draw a free body diagram of each block individually. You're going to recognize that the acceleration on the one block is the same magnitude as the acceleration on the other block, just in different directions. And you're also going to recognize that the force of tension on the one block is equal to the force of tension on the other block, but I've got those absolute value signs on there again because they're in two different directions. We don't want to get confused on like it's positive on one and it's negative on the other, or in this case they're both positive, and I don't want to have to deal with whether the negative sign is confusing me or helping me. It's supposed to help me. So how is it going to help me here? If I take this situation like this and I say that as the red block drops, the blue block will move to the right, I already know what direction these two blocks are moving, but what if I move the red block up here just to make the math easier on me? Conceptually, that doesn't throw me off. I think I understand exactly what's happening here. It's like the pulley somehow bent my coordinate systems, my x-axis, and mathematically this will work out as long as I'm careful about establishing at the end what is positive and what is negative. So the net force acting on the system is the mass of the system times the acceleration of the system. But what's the net force acting on the system? I have tension pulling to the right on one of the blocks and the exact same tension pulling to the left on the other block. It's an internal force. So I could say T is positive on one of them and negative on the other one, and they would add up to 0. Or I could just say it's an internal force and I don't want to have to include it. Either way, the net force on the system is mass 1 times g. That's the only force on the system that's causing the system to accelerate. Mass 2 times g and the normal force are both there, but they're not causing the system to accelerate in a direction that it's free to move. The mass of the system, of course, is mass 1 plus mass 2. And when I therefore calculate the acceleration of the system, I get 3.05 meters per second per second. If I go to the website that I can say show numerical values, and it shows me the acceleration is 3.05 meters per second squared. And the blocks move in the direction I thought they would. No surprise. So I hope it makes sense how you would calculate a problem with an Atwood's machine or with a modified Atwood's machine. Please come ready to class prepared to work on a problem like the one shown here, a combination of a modified Atwood's machine plus an inclined surface, and it's possible that the surface has friction with the mass that is on it.